All right. So previously in last class, we talked about a graph search strategy called the breadth first search. Okay, where essentially we keep exploring new node, but then we always expand those that we discovered earliest first. Okay, and this already can be used to check for example, connectivity of graph or check whether you can reach a node from a source node or not. Okay, so today we're going to focus more on the property of this BFS search strategy. It turned out that in addition to help us to traverse the entire graph, BFS also give us something extra. Okay, in particular, this is related to compute the so-called shortest path in a weighted graph, which we introduced at the end of class last time. But just very briefly, what is the shortest path? Well, if given the graph, and given the path in the graph, the length of this path is simply the number of edges inside, okay, which is also equal to the number of nodes in this path minus 1, okay? And the shortest path from U to V is just a path from U to V with smallest length, namely, you want to reach from U to V using smallest number of edges, okay? And in general, this shortest path may not be unique, okay? And the shortest path distance from U to V is simply the length of the shortest path, namely, what is the smallest number of edges needed to go from U to V, okay? So this is a natural question because very often, say when you try to arrange schedule of flight, you want to not only know whether you can reach from Columbus to Denver or not, you also want to find a way to fly from Columbus to Denver using smallest number of connections, namely smallest number of edges. And that basically means you want to find the shortest path from Columbus to Denver. Okay, all right. And we also mentioned that their shortest path has some properties of shortest path. Number one, our shortest path has to be simple. Okay, namely, every node can only be visited the most exactly once. So a path like this, that you visit the same node twice, will not be shortest. Okay, because if really I have a path like this, I could have gone from U to W and then to V directly without taking the detour. Okay, so the second property is that a shortest path, if you have a shortest path, then any subpath, you take any subpath, say from W1 to W2, that must be shortest path from W1 to W2 as well, okay? And as a consequence of this, okay, a simple implication is that if you need to take V, the shortest path going from V0 to V equal to Vk has k edges inside, okay? Then that means that this path can be decomposed as the shortest path going from V0 to Vk minus 1 first, consisting k minus 1 edges plus 1 axial edge, okay? So it's a very simple observation, but what it's saying is that to reach a node which is at distance k away from the source, you have to first reach a node which is at distance k minus 1 away from the source and then extend it by one extra edge, okay? And this simple observation actually is behind the idea to compute the shortest path, okay? So that's what we're going to talk about now. How do we have an algorithm to compute the shortest path? In particular, the high-level idea is simply that if I want to compute the shortest path from the source node S to other nodes, okay, what I can do is that I can first find all the nodes that's distance 1 away from the source nodes, okay? So then those basically that S can reach using 1 edge, okay? Then using this node, I'm going to now explore this distance 1 node and then use them to find all the nodes that's a distance 2 away from the source and so on. Okay, so then I'm going to use all these nodes that are distance 2 away from the source, use them to help us to find all the nodes that are distance 3 away from the source, okay, and so on. Now, why does this idea work? Well, in general, what we're saying is that because we know that to get to a node at a distance k from the source, I have to first reach a node that at distance k minus 1 from the source, and then extend it from this k minus 1 away, this node at distance k minus 1 from the source, find the edge to this new node. Okay, so that means that I have to first find all the k minus 1 distance nodes from the source and extending them to find those at that distance k from the source. Okay, so this is what we're leveraging here. Okay, all right. Now let's just look at an example, and then let's talk about the algorithm to do that. Okay, so in this example, our source node is S. Okay, in other words, S is at a distance 0 away from itself. Okay, so now what does the algorithm do? The algorithm says first, let's find all the nodes at a distance 1 from the source. And that basically are all the nodes that are neighbors of S, right? Because they're connected by one edge. So this that we explore this 2 edge and then identify 2 neighbors, A and C, and then this at distance 1 away from the source. So that's what we want to do first. Okay. Next step, we say that, okay, let's take those nodes that are distance 1 from the source and then find that who are at distance 2 from the source. Okay. And from A, we look at its neighbor, and then it has only one neighbor, that's E. So we found that E must be at distance 2 away from the source. Okay. All right. And at C, we'll also explore its neighbors. So, and C has 2 neighbors, E, but we already found the E, means that we already found a way which can reach E, either the same number of steps or faster, okay? And also G. So G is also at a distance 2 away from the source. Okay, let me just comment that suppose I also have the edge going from C to A, okay? Suppose I am modifying the graph here, okay? So suppose this edge is also in, then when we explore C, we will also discover, we'll also reach A again, okay? But that means that we found a new way to go from C to A using 2 steps. But we notice that A already was discovered, namely already identified faster way to reach it before, okay? You can think of the time we visit the node correlates the how fast we can reach it, okay? So in this case, this edge will do nothing. We didn't find a new path, okay? So now by exploring A and C, we find E and G at a distance 2 away from the source, okay? All right. Now we want to discover all the nodes at distance 3 and not shorter away from the source. And from that, we know that we only now need to look at the nodes that's already at a distance 2 from the source and then explore their neighbors. So because it has to be reachable from a node which is a distance 2 away from the source. Okay, so we take E, and from E we find that we can reach B in 3. That we haven't seen B before, so B is reached in 3 steps. Same for H. It's also 3 steps. Okay, and that's all that E can help find. Okay, then from G, I explore the neighbor of G and I find F. And also H again. But we already found the H, so we didn't find anything new. Okay, so now after we explore E and G, I know that I must have discovered all the nodes that are at most the distance 3 away from the source, because they can only be neighbors of those distance 2. Okay, so now we can move on. Let's say that we try, oops, I missed the one from G. I can also find I, which is also distance 3. Okay, then we say that, okay, let's now see whether we can discover any nodes which are at distance 4 away from the source. So for that, we need to start with those nodes that's at distance 3 from the source, okay? So we go through them one by one. From B, we only find A. But then A is already discovered, so we didn't find a new node. And then we have F, we discovered C, same, C is already discovered, so nothing new. And from H, I discover A, and G is already discovered. And from I discovered H is already discovered. So after this, we explore all the neighbors of those at distance 3 from the source. we didn't find any new nodes. That means that we didn't find any nodes at distance 4 away from the source. So we're done. Okay, that means we explored everything we could. Okay, we finished the procedure, and this is the output. Okay, so this is what we did. All right, and if you look at the procedure we just did, and you may realize that, wait a minute, this exactly is what the breadth first search algorithm was doing, right? So intuitively, so here's the breadth first search algorithm, the code, just to remind you, okay? So remember that in breadth first BFS, we first, after we first find a node, okay, we change it from undiscovered to pending, okay? You can think that is the first time that we found a way to reach this node, okay? And the way then we explore this node is that we explore the oldest pending node first, okay? So intuitively, the time that we discover a node, okay, changing status from undiscovered to pending, essentially it relates to the fastest way to reach this node, okay? And by exploring those oldest pending nodes first, that means that we first explore those with the smallest distance to the source first, okay? Basically, that means in the previous example, from S, after we reach A and C, you can think that this is all distance 1 from the source. Then we will explore this oldest one, namely those distance 1 away from the source node, source first, to get a new node, okay? And this guaranteed that when we discover new node, this is the shortest way to reach it, okay? All right. So more precisely, okay, the BFS algorithm guarantees that, okay, through the execution of the algorithm for any integer k, okay, any nodes at a distance k from the source are going to be added to the queue before any nodes, of distance. Here it should be of distance bigger than k. Okay, so all nodes at the distance k away from the source will be added to the queue before any nodes of distance bigger than k. Okay, and in other words, the nodes are added to this queue of pending nodes, okay, in increasing order of their distance to the source. Okay, so, and because of that, this essentially is implementing the idea we said that we are in the queue. The order of them essentially is the increasing order of the distance to the source, and by processing those oldest first, that means that we first processing those at distance k away from the source before we will then process. That will help us to discover those at distance k plus 1 from the source and added to the queue. Okay, so all right. Or maybe let's just look at a case analysis. Okay, in particular, consider in the BFS algorithm, okay, we popped a node from the queue. Namely, we take a node currently with the oldest pending time, okay? And assume that the distance from this node, so where this is a source S, and we popped a node U, and assume that right now, the distance from U to the source is K, okay? Now, what does the BFS algorithm do? The algorithm then says that, okay, let's look at all the neighbors of U, okay? Because if this node can be reached from the source in K steps with K edges, okay, then that means their neighbors can be reached within K plus 1 steps with K plus 1, a path of K plus 1 length, okay? So that's why we're going to check everything, we want to find all the shortest paths of length K plus 1 going through U, basically, okay? So we look at its neighbors, okay? And if a neighbor V of U if this one we haven't seen it before, with the status is still undiscovered. What does it mean? That means that we now found a way to reach V through U using only k+1 step. Okay, and this is intuitively the shortest. This must be the shortest path. Why? Because that if it's not the shortest, let's say that there was another node W, okay, that we could have gone from S, I'm going to use blue color, to W, and then from W to V through an edge. If this is a shorter path, okay, that means that the W has to be at a distance smaller than K from the source, okay? But because we always processing the oldest pending node first, that intuitively means that we should have already processed the W. And when we were processing W, when we're exploring W, we should have already discovered V. So V wouldn't be left undiscovered, okay? Since this is the first time we discover V, that means that W cannot exist. There's no shorter way to reach V, okay? All right, so we look at the neighbor V of U. If V is undiscovered, okay, that must mean that we found the shortest path reaching V. And the length of the shortest path is basically the length of U plus 1, K plus 1, okay? Again, this comes from because we always explore the oldest pending node, namely those are closest to the source first, okay? So that by the time we explore U, inductively, we have already explored all the nodes whose distance is smaller than U, smaller than K, okay? All right, now, if, on the other hand, that this V, we discovered a node V, and this V is, the status is either pending or is visited already. What does it mean? That means that I have already found a way to reach V, okay? And that, so, and the path that I have found cannot be more than K plus 1. Why? If this was, because that that means the V must be found through some other nodes, and that nodes, since we already explored that nodes, that distance can be at most K. So we have the length to V is at most K plus 1, okay? That means that we didn't find any new way to reach V, okay? So we do nothing to V, okay? So we only change the shortest path status when we discover a node V, which is still undiscovered, okay? All right, questions on this? Okay, and once we understand this, okay, it's easy to modify the breadth first search algorithm to make it also record the shortest path distance information, okay? In particular, now I'm also going to use a new dictionary distance to store the discovered distance to the source, okay? At the beginning, all the distance to the source is infinity, let's say, because we don't know yet, we haven't found it yet, okay? The only distance that we know at the beginning is the source node, okay? The distance to itself is 0, okay? Then we take the oldest pending node, then we start to explore its neighbor, okay? Now, if the neighbor V is undiscovered, that means that we found a new way to reach V, okay? So we change the status of V to be pending because we discovered it, but we haven't yet explored it yet, okay? And what is distance to V? Well, the distance to V is basically the distance to U plus 1 through the edge UV, right? So it's distance to U plus 1, okay? So that's what we discovered, okay? And we added V to the pending list, okay? And after we explore all the neighbors V of U, we change the status of U to be visited, same, the standard, okay? The only difference we add is that we have this to update the distance, maintain the distance to the source node, okay? All right. Okay, But we can also actually record a bit more, which can also later help us to recover the shortest paths themselves. Okay, not just the distance, shortest path distance from the source to this node. We can record information which can help us to retrieve the shortest path as well. Okay, in particular, what we're going to record is that for every node V, okay, not only we record its shortest path distance, we also remember, okay, who is its predecessor along some shortest path. Okay, in particular, this we call BFS predecessor of a node V is basically that suppose you first discovered V when you are exploring node U. So this is the first time you discovered V. Okay, then we call U, we set U to be the BFS predecessor of V. Okay, why? Because the first time you discovered V, that's when you discovered the shortest path. Remember, if the distance to U is K, then the distance to V will be K plus 1. Okay, so in other words, at this point, you found a path which is consists of the shortest path from S to U plus UV. And this is the shortest path to reach V. Okay, as such, U is a predecessor of V along the shortest path. Okay? Okay. Now we call this BFS predecessor because in general, there may be multiple shortest paths. And we're talking about specific shortest paths discovered by the BFS algorithm. Okay? All right. So now if everyone remember who is its predecessor along the shortest path, then we kind of trace back the shortest path. Okay, so we want to record this predecessor information as well. Okay, in particular, right, this is just repeating what I just said. U is the predecessor along a shortest path from the source S to V. Okay, and the shortest path from S to U, basically S to V, consists of the shortest path from S to U plus the edge UV. Okay, now we can easily modify the code to remember predecessor information. In particular, we use another set to record the predecessor, and all we need to do is that one way. Remember, this is when we first discover. If we get into this if condition, that means that's the first time that we find discovered V, find the shortest path from S to V, okay, from the source to V, okay? So we are not only in that case record the distance, shortest path distance to V, we also record that predecessor of V equal to U because we found V when we were exploring U, okay? That's the only difference, okay? All right, so now what we have here is basically both a breadth-first search algorithm. This also can be considered to be a shortest path algorithm from the source node, okay, in both direct and indirect graph, okay? All right. Now let me just use this example again to show that what are the predecessor information that we're remembering and how to later use this predecessor to get to the shortest path, okay? So again, let me use the red color. So at the beginning, all the distance for all the nodes are set to be infinity, other than the source node, whose distance is 0, okay? So everything that I'm not marking right now, they are distance infinity at the beginning, okay? Now, I'm going to use blue color to indicate when we explore an edge to find a neighbor, okay? And I'm going to later use red to mark the predecessor information, okay? So at S, okay, I explore its neighbors. So I explore both this edge and this edge, okay? And both of the nodes that I found, they are, right now, they are undiscovered. That means that I found a shortest path to them, okay? And as such, our algorithm set the distance to A to be distance to S plus 1. That's 0 plus 1, that's 1. And the predecessor of A as such is S. And I'm going to use the backward arrow, red arrow, to mark this, okay? So that means that the predecessor of A is S. Okay, this means predecessor. I'm just using this to mark it here, okay? Same, I found C, and that means the distance to, then this one was undiscovered before. So now this one is going to change to pending, both are pending. And the distance to C is 1, and the predecessor of C is set to be S. Okay? All right. As I said last time, in all the convention for this graph search strategy, okay, when we have multiple neighbors, we assume that they are always stored in increasing order of their labels. Okay, so when we explore the neighbor of S, we explore them in order of the increasing order of lexicographically their label. So A will be explored first, then C. Okay, so when we add, the A will be added to the pending list first, and then C. Okay, so in fact, maybe let me just like before, let me still put the pending here. So now in the pending list, we have A and C. Okay, now our algorithm says, now let's pop the oldest one in the pending list, which is A. So we take A out. Okay, we're going to process A. And then we're going to look at all the neighbors of A. Okay, now A has only one neighbor, which is reaching E. And E right now is undiscovered. That means that we now discovered E, we put it into pending. And the distance is the distance to A plus 1, because I can reach E by through first reaching A first and then plus 1. Okay, so the distance to E is 2. Okay, and E was discovered when we exploring A, so we put the predecessor to be this. Okay, next, and there's no other neighbor of A, so we're done with A. Okay, so A status is changed to be visited. Okay, and when we're processing E, we now add the E to the pending list. Okay, next, we take the next from the pending list, which is the other one whose distance are 1 away from the source. Okay, now we explore C, and we first discover neighbor E. Okay, but E is already pending. So even though that we explored this edge, but then E is already found. Okay, so we do nothing. Okay, so the predecessor of E remains to be A. Okay, and then when we explore the edge CG, we discover a node which was undiscovered. So we found a new way to reach it, and its shortest path distance now is 1 plus 1, that's 2. Okay, and the predecessor of G is C. Okay, and we continue. Okay, I will not go through. So now we add G into this, and then next, as you can see, now E and G are at distance 2 away from the source, but we will not pop any explore any nodes at a distance 2 away from the source till we finish exploring all the nodes that are at distance 1 away from the source. Okay, so this is basically intuitively by doing the exploring the oldest pending nodes first, we kind of first explore all the nodes at distance 1 away from the source before we move on to explore nodes at a distance 2 away from the source. Okay, and so on. Okay, all right. So if we continue this process at the E, we will be able to identify B, and then B's predecessor is E, and B is distance 3 from the source, and the same as we'll find H. So H predecessor is E, and this is at distance 3 away from the source. And at the G, we'll find F. So, and F, the predecessor is G, and the same we'll find I. I, the predecessor is G. Okay, and that's it. Okay, that finished exploring the entire graph. Okay, so in the end, you see that the red edges record the predecessor. Okay, now if you ask me, you said that, okay, I know that I can reach from S to I in 3 steps. Okay, but what is the shortest path itself? Okay, what do we do? Well, for me to retrieve the shortest path, I just go to I, says that who is the predecessor? G. Okay, so that means G is the one before I along the shortest path. Then we say, who's the predecessor for G then? Because then I find the best way to reach G. So that's C. And then we ask the same, who's the predecessor for C? That's S. In other words, the shortest path, and to report shortest path, now you report in the opposite order. The shortest path from S to I as such is basically S to C, and then C to G, and then G to I, okay, by using this predecessor information, okay? So remembering both the distance and predecessor, we can recover not only the shortest path distance, we can also recover the shortest path themselves, okay? All right. Note that as we said, shortest paths are not unique. For example, if I ask what is the shortest path from S to E, okay, then we follow the predecessor. We say, okay, E predecessor is A, and then A is S. In other words, from S to A and from A to E is the shortest path to E, and this is the one that discovered by the breadth-first search, okay? But we note that, in fact, from S to C, C to E is another shortest path, right? But this is not the one that recorded by the BFS algorithm. Okay. Now, however, when you are exploring C, if you find a discover node E, which is pending, whose distance is the same, which is also 2. Okay. Intuitively, you know that you discovered another shortest path to E with only 2 steps. Okay, shortest. So you discover another shortest path. Okay, it's just that the BFS doesn't remember that information. Okay, in your homework, you will have a problem which is essentially asking you to actually count the number of shortest paths reaching a node, say reaching E. Like in this case, you should remember 2. Okay, you are asked to think about how can you further modify the BFS algorithm to collect this information. All right, all right. Okay, now the time complexity of this shortest path algorithm, that's the same as the BFS algorithm because there's nothing different. We're having essentially the same algorithm. We just added a few lines, constant, for when we're processing each node, we just add a constant extra complexity, okay? So the time complexity is still B plus E. Note that this is the optimal in the sense that even just to store this graph, you need a V plus E space, even if you just touch each one once, okay? Asymptotically, you need a V plus E time.